Okay, good morning everyone. I'm Alessandro, a PhD student at the EDF lab, supervised by Michel, Thierry Fouquet, and Maria Teles. And today I will be giving you, if the slides turn, I will be giving you a presentation about the first part of the work that I've done as part of my PhD thesis. The subject of the thesis in general is the better address the problem of the four waves interaction and then eventually also the three waves interaction. And for this first part, what we'll try to do is understand the dynamics of C spectra under the only effect of the four waves interaction. So just to give a little bit of context, the frame of this work is the Tomahawk code, which is a wave model, a third generation wave model, where as we have seen multiple times, we have an energy balance for the wave action and source terms, or more exactly, including also energy transfer terms as here I call it QNL, it's been called SNL so far, so sorry for that. And so today in this work, I will talk to you about the results of simulations run of the conservative Hasselmann kinetic equation, where the only term that appears is QNL, as you can see. And it's important to highlight that the simulations we ran were only run in one point in space. The initial conditions were, we will see this better afterwards, but the initial conditions were completely arbitrary, and deep water conditions was assumed for is assumed for all the following. So luckily I don't have to go too much into details about how numerically compute the QNL term, as Michel gave a presentation earlier on this morning. But so I will just list the methods that we used for this work. Particular focus is on the GQM method, which, as we understood, is a quasi-exact, so it tends to the exact solution. But we'll also compare the results with the simulation runs with DIA and multiple DIA methods. So here it's just to present the numerical setup. So the parameters that we chose for the simulations, you can see the refinement of the frequency direction grid. As you can see, the physical time simulated is quite long, almost 1 year, and this could be done thanks to the use of adaptive time step that reduced the overall CPU time. And regarding GQM, the results are obtained with the so-called medium resolution. So as quickly Michel mentioned, a part of the configurations were filtered out. So here, as I was already mentioned, the initial conditions were, which we set them completely arbitrarily. So in particular, we chose 4 cases that are here listed with their formulas and visualized in these 2 plots. Case 1 and 2 are, I would say, less realistic, as the frequency shaped spectrum for case 1 is a step shaped, case 2 is a Gaussian. With a half plane, we call it half plane spreading, angular spreading. And cases 3 and 4 were both Jones-Swap frequency spectra with different width of the angular spreading. So we may move on to look at the first results. The first thing we looked at was the evolution throughout the simulation of the representative C-state parameters. So on the right, you can see the significant wave height at different time steps divided by the initial wave height. As you can see, there is an apparent loss of energy, which doesn't make sense because the equation is meant to be conservative, but this is due to the fact that there is the energy transfer due to the four waves interaction brings also the energy outside of the domain that is discretized, so this results in apparent loss of energy. And on the left, you can see the evolution of the peak period. The results are here plotted for the colored lines are for the GQM simulations, and for DIA and multiple DIA, we only reported case 3, so it was a beginning Jones-Swap spectrum, while GQM, it's all the 4 initial cases. And the solid black line are the theoretical predictions that were obtained by Ardhuin et al. In the paper of 2005. And as you can see, for all methods and all cases, the slope almost fits well with what was predicted theoretically. Another parameter we looked at is the angular width. And here we begin to see the first differences, because as you can see, the four initial cases simulated with GQM, even if quite slowly, but at the end you can see a similar trend that at the end of the simulation arrive to close value between each other, while the DIA and MDIA simulations move towards more wider spectra in the frequency in the directional spreading. Another thing we wanted to look at is the width, but this time of the frequency spectrum. And in order to do that, we picked two parameters, QP and lambda, that then was also normalized. And also here you can see that the four initial cases simulated with GQM at the end of the simulation also arrive to a similar solution between each other. While DIA and MDIA once again arrive to different solutions that are also wider, so also in the frequency and the frequency grid. Recalling the paper of Ardhuin that I mentioned earlier for the theoretical results, we wanted to investigate the self-similarity of the solution of the Hasselmann conservative kinetic equation, that are solutions that can be written in this form, where in particular we see appearing a function u that we will call a spectral shape function that is stationary, so it doesn't vary with time. So what we did was, thanks to the rescaling coefficients alpha and beta found by Ardhuin, what we did was computing the function u at different times over the simulation to check its stationarity, and therefore the self-similarity of the solutions. So here is the result for the case 3 simulated with GQM. You can see an animation throughout all the simulation and a superposition of different time steps. What we see is that there is a beginning transient period, I would say, that lasts around half an hour, during which the function u changes a lot. And this is, we will see also this little bit better afterwards, but this is because we begin from a state that is very far from the equilibrium state. So the spectrum is evolving very rapidly. But afterwards, we see that the function is indeed stationary, and so the self-similarity is proven. The results for DIA, this is the same case simulated with DIA and multiple DIA, that more or less, but like we can see that function u is quite stationary in both cases. So self-similarity is also proven also for these methods. But physically, the self-similarity of the solution of the Hasselmann kinetic equation means that the shape of the spectra described by the function u is not supposed to vary in time. So here is, for case 1, so beginning from a step-shaped spectrum simulated with GQM, we put two different phases of the evolution of the spectrum, a short term, we can call it on the right, and long term on the left. And in particular, in the long-term evolution, we see that once near equilibrium shape is reached, it is constant for all the simulation, and we only observe a shift towards lower frequencies of the spectra. So what we could have guessed by looking also at the C-state parameters is that, at least for the simulations run with GQM, so for all the different initial cases, the final results, so the final spectra at the end of the simulation, were very similar to each other, meaning that the solutions converged towards the same final spectra. And this is what is shown here. Here we have the spectrum for the 4 different cases integrated in azimuth and frequencies. And in particular, we can highlight the tail of the spectra that is proportional to the frequency to the power of -4, as predicted by the theory also.
Just a comment. This is
Yeah.
not isotropic, right? So this
No,
is
it's
so
not.
so
Yeah.
it works
It's
also.
arbitrary initial conditions, and the initial spreading is not at all isotropic.
Okay.
This is, on the other hand, the comparison of the final spectra for the same initial case, case 3, Jones-Swamp initial spectra, for the 3 different methods used for the study. And we see, in particular, in the integrated, in the frequency, we see some discrepancies in the results that maybe we can address better when looking at the 2D spreading function, where we see an animation for it's still case 3 with GQM, and in particular we can see that throughout the simulation there is a bimodal structure that appears while we begin from what we imposed, that was unimodal, and this bimodal structure is at the end of simulation at least is limited to a range of frequencies that is just before 4 times the peak frequency. And this is what maybe we can see also even better here. This is for all the 4 initial cases, even if we already saw that the final spectra were really close to each other. At the final step with GQM, this is the not normalized this time spreading function, D, at different frequencies. And we clearly see the bimodal structure that is formed. But then it goes back to unimodal beginning from 4 times the peak frequency. But does this happen also with the other method? And well, yes and no. This is the final result of the spreading function simulated with the 3 different methods, and we can see that in particular for the DIA, the results are quite different. There is still a bimodality at the low frequencies, but then there is a general broadening of the spectrum for higher frequencies that is quite different from the results obtained with GQM. Multiple DIA is closer to GQM, but still we can see that there are some discrepancies. So finally, what we wanted to show you is just an example of application of the GQM method. So what we did was taking ANEMOC3, which is a hindcast model based on the Tomahawk code that simulates past conditions of the C states. And what we did was running simulations for the month of February 2014 with the GQM method and DIA method without changing the other parameters. Here you can see some the specificities of the grid of ANEMOC3 that you can see covers the whole Atlantic Ocean, and it's more refined close to Western Europe. And what we present here is just briefly rough comparison of the CPU time for different number of processors. Here it's a log scale. And what we found also was mentioned earlier by Michel. What we found is in optimal conditions, so the number of cores was different for the 2 cases. We found a factor between the 2 simulations, 2 CPU time of around 15. So I'll let you draw the conclusions about that. And so finally, I would like to end, if I still have time, for telling you the next steps that we would like to do. So what was also mentioned this morning, we would like to try to see, use a model of an extended kinetic equation, in particular to compare the results for the short time spectrum evolution that, as we've seen from the theory, should not theoretically be modeled by the Hasselmann kinetic equation. Then what we also would like to do is to reproduce a fetch limited case and do a study similar to this one. That is what we can call a duration limited case. And then finally, the more, I don't know if more important, but the more long-term goal would be to optimize the GQM method in terms of CPU time, and then extend its applicability to finite water depth conditions, and including also ambient current. So thank you for your attention.